All right, this is a video review key for our atomic structure. We're starting off with a mass spectrometer calculation so that we can get the weighted atomic mass average. I've got the data recorded here, but let's go to the spectrum and see where this data comes from. So here's our spectrum. We have 70 for one of the isotopes, and the relative intensity is this red number on top, 56.19. And then the 72 has a relative intensity of 75.16. The 73 has a 21.25. The 74 is 100. And the 76 is 21.22. So these numbers will go in column 1. The maroon numbers will go in column 2. Let's see what that looks like. So here's all of our isotopes right here. Here's all of our relative abundances. Now what we do is we add this column up to get 273.82. And from there, we will divide each of these numbers by that 273.82. So this one's on top, this one's on the bottom to get 0.2052. And then this one divided by the 273 one more time, we can get 0.2745. And then we just keep going down the column to get each one of these numbers. To get the mass contribution, you take the isotope value, 70, times that decimal percent. I like to call it a decimal percent to get 14.36. Okay, and 72 times that decimal percent to get 19.76. And likewise, just keep doing each one of them in this column multiplied by each one of this column. And you get all these numbers. Add it all up, and you get a relative or a weighted atomic mass average of 72.69. And if you look at the periodic table, that is the element germanium. And that's how you do the weighted atomic mass average calculation. Okay, let's move on then. We have 3 experiments that we talked about, 3 primary experiments. One is the cathode ray tube. This one is J.J. Thomson. An electron beam was traveling through and it reached these charge plates, and the electron beam bent down. It was discovered that electrons are very light and they are negative in charge. We moved then to the Robert Millikan experiment, where an oil droplet was suspended in midair between 2 charge plates, and the electron's charge was discovered, 1.6 times 10 to the minus 19 coulombs. And then finally, the all-important Rutherford experiment with the gold foil. Alpha particles were shot at the gold foil. Most went through, some were deflected back. And the nucleus was discovered, and electrons were orbiting the nucleus like the planets do our sun. So let's go through our descriptions and see if we can identify what experiment they are. So the electrons are negative, that's the J.J. Thomson experiment. The charge of an electron was the Robert Millikan experiment. The nucleus was the Rutherford experiment, and so were the protons. The experiment that determined electrons are light is the J.J. Thomson experiment. The one that electrons orbits a nucleus, that's the Rutherford experiment. The mass of electron was determined by, actually it is a combination of Robert Millikan, so number 2, along with J.J. Thomson, number 1, but we'll just put 2 for that one. Protons are positive, that is the Rutherford experiment. Robert Millikan did number 2, the oil drop. Ernest Rutherford did number 3, the gold foil. J.J. Thomson, the cathode ray tube, which is number 1. Which experiment used electric plates? That would be Robert Millikan, number 2. Also, it could be number 1. J.J. Thomson used charge plates too. But I guess we'll go with just number 2 because that was the primary part of the experiment for Robert Millikan. Which one suspended oil drop? Number 2, Robert Millikan. Deflected electron beam, that was number 1, J.J. Thomson. And alpha particles, that was the Rutherford experiment. So who got Nobel Prizes? All 3 of them, 1, 2, and 3. So J.J. Thomson, Robert Millikan, and Ernest Rutherford all got Nobel Prizes. All right, now we've been doing electron configurations and we've been following 3 rules. Let's see what those rules are. So the first one, the question is, what principle does the following electron configuration violate? Well, we look at this 1s2, 4s2, 3s2. We notice that this is way out of order. We should be going 1s2, 2s2, 2p6, etc. So that's off-bot ordering. So whenever we do the ordering correctly, it's called off-bot ordering. If we violate it, then we violate that principle of off-bot ordering. What about the next one? Well, this is called the Hun rule. So when we do not keep them separated, that violates the Hun rule. The Hun rule says we will separate electrons as much as possible. We would not leave an empty orbital here and do two pairs here. This would be one pair and one by itself and one by itself. So whenever you don't do it correctly, you're violating the Hund rule. So keep them separated. Next principle here, we've got arrow up, down, but then on this one, we have an arrow up, up, where it should be arrow up and arrow down. That is the Pauli exclusion principle that's being violated there. Pauli said no two electrons can have all the same quantum numbers, okay, in the ground state. What does that translate into? You have to go arrow up and arrow down anytime you have two arrows in one spot. All right, next. Name one way an electron is a particle. Well, it has a mass, 9.11 times 10 to the minus 31 kilograms. And then what about a wave? Well, they have wavelengths. De Broglie said the wavelength of an electron is equal to Planck's constant h divided by mv, the momentum of the electron. So they have a wavelength, therefore it's behaving like a wave. All right, now let's go on to our amplitude, frequency, speed of wave calculation. So I actually took a ruler out and I measured the amplitude of this wave from the center line up to the top of one peak, and I got 1.3 centimeters. So I actually measured it on my paper. Now I could have gone from the center line to a trough down here, and I would have gotten probably, hopefully 1.3 centimeters. Okay, determine the wavelength for the wave. Well, what you do there is you measure the distance between two crests. For one crest to the next crest, I measured to be 1.3 centimeters, so the same as the amplitude. Now, you could have measured between the two troughs as well. All right, what about getting frequency? Well, you got to count the number of bumps you see, number of bumps you go through, and divide it by the time. So let's count that. That's 1, 2, 3, 4, 5, 6, 7, 8, 9 bumps. And the time is 0.009 seconds. So we take 9 divided by 0.0090 seconds, and you'll get 1,000 hertz. And here's my calculation for that. 9 divided by 0.00900 equals 1,000 hertz. Now, the speed of a wave, you multiply the wavelength multiplied by frequency, and then you get, well, this is accurate or precise to one significant digit, 1,000 centimeters per second. You could have 1,300 centimeters per second also. So you can keep two sig figs if you want to. Okay, but anyways, the speed of a wave is always a product of wavelength times frequency. All right, now let's go on to our calculations for waves. So let's use the grid below, okay, for the colors of copper and determine their energies and wavelengths for each light. Well, we're using the color key here. The first color we need to find is blue. So I go down here, blue is 450 nanometers. And then green, I go down here, it's 495 nanometers. Okay? So remember, nano means 10 to the minus 9. Now to get frequency, you got to take, so frequency is new. Remember what I said in class, what's new? It's c over lambda, the speed of a wave divided by wavelength. But the speed of the wave is 3 exponential 8. The wavelength is 450 exponential minus 9 equals 6.7 exponential 14. Now remember, the exponential means times 10 to the, it's just easier to write the e there. And that's also how you want to enter this in your calculator anyways. When you're done with that, you would multiply that frequency by Planck's constant, 4.14 e minus 15, and that turns out to be 2.8, and the energy units are called electron volts. Electron volts is much more useful to use for atom jumps or electron jumps. We'll do likewise with our 495, so 3 exponential 8 divided by 495 exponential minus 9 gives you 6.06 exponential 14 for the hertz, the frequency, and multiply again by Planck's constant, you get 2.5 electron volts. Now it says fill in the spectral lines for copper. So what I did is I estimated about 450 and I drew a line, and I estimated 495 and I drew another line. So these are the two lines. This is the blue light and this is the green light on the spectral chart. So in other words, if you were pretending to be looking through a spectroscope, okay, what would the lines look like for copper? And that's what they would look like. That's not all the lines for copper though. Okay, next. All right, so we have the energy diagram for lithium positive 2. We see the ground state n equals 1 is negative 122.4 electron volts. So what if an electron jumps from n4 all the way down to this n1? Well, it says 10.8 nanometers of wavelength is released for this. So we need to do the same calculations. 3 exponential 8 divided by 10.8 exponential minus 9 gives you a frequency 2.78 exponential 16. Multiply that by Planck's constant again, we get 115 electron volts. So this is just like what we did above. But now to determine n equals 4 energy, you got to take the base, negative 122.4, add the 115 to it, and this is negative 7.4 electron volts. So n equals 4 energy level is negative 7.4 electron volts. Now remember, all the energies are negative because electrons are negative. All right, so let's move on. Next one is we're dealing with our electron configurations, and we're dealing with protons, electrons, and neutrons. So 10, simple as Sn. If you look at its atomic number, it is 50, so it has 50 protons and electrons. It has an atomic mass of 119, so if you subtract the mass from the atomic number, you'll get 69 neutrons. Likewise with bismuth. Bismuth has an atomic number of 83, so therefore you have 83 protons and electrons. And whatever the atomic mass is, minus 83 will give you 126 neutrons. So that's how you fill that chart in. And last but certainly not least, our noble gas configurations for the electrons in the atoms. We're starting with arsenic here. Let's find arsenic on the periodic table. Arsenic is right here. It's in the P3 column. Remember, it goes S1. This is S2. This column's P1, P2, P3, P4, P5, P6. So arsenic is here. We're in the P3 column, so that is the fourth row down, 1, 2, 3, 4. So we are 4P3, but remember, as soon as when you write a P3, you've got to have an S2, so it must have a 4S2 with it. Okay, we'll go up one and over to get the noble gas. Always go up one row and go over all the way. So we're argon, okay, 4S2, 4P3. And let's take a look at what that looks like. So argon, 4S2, one line, arrow up and down, because an S only has one line. Remember, there's P has 3 lines, 1, 2, 3. We'll keep them separated, so arrow up, arrow up, arrow up. That corresponds to 5 total dots. 2 plus 3 is 5. We should have 1 pair and 3 separates. 1 pair and 3 separates. It shows you right here, there's 1 pair and then 3 separate arrows. These 3 dots represent the dots, the arrows here, the electrons that are there. These 2 are represented right here. All right, next one is thallium. So let's go back to our periodic table. Thallium is located here. That's in the P1 block, or P1 column. We go over here and find that it's a 6P1. As soon as when I write a P, I have to have a 6S2. So 6S2, 6P1. I go up and over. That would be xenon for the noble gas. So let's go back to our answer key. So we have xenon, 6S2, 6P1. So the 6S2 only has one line, arrow up and down. All S's only have one line. Since there's 2, arrow up, down. The P will have 3, 1, 2, 3. 1 arrow up. That represents in our dot diagram 2 dots there and 1 dot. So the 2 dots together and 1 dot, just like the pattern right here. And lastly, but certainly not least, we've got barium. Barium over here. We're in the S2 column, and we're down in the 6th row, so 6S2. Go up all the way over here. Xenon, again, is our noble gas. So I'm expecting to see 6S2 with a xenon in front. So xenon 6S2, again, arrow up, down. And there are, because there's 2 electrons in there. And that represents just 2 dots, because those 2 electrons are paired there. All right, that does it for our review. We'll deal more with in class tomorrow. And our test will be coming soon.